Hello everyone and welcome in today's video wherein we will be learning the graphical representation between the three terms, important terms, that is position, time and velocity. We will learn as to how do we actually depict the graphically, how do we depict the relationship between the three terms, right? And to understand the graphical representation, this is the kind of graph that we will consider. So what kind of graph is this? First of all, understand that this is a velocity time graph wherein the velocity is on the y-axis. So this is what is y-axis and the time is on the x-axis, right? So this is a velocity time graph, and we discussed in the previous videos that whenever we consider any area under velocity time graph, it gives us distance or displacement, right? So now let us learn how to read the graph. So in this case, we have considered that there is an object, there is a body which is initially traveling with a velocity of u. So this distance AO, let's say it is the initial velocity with which the body is traveling. And after traveling for some time, let's say this is the x-axis is the time, so OC becomes the time. So after traveling for certain time, the object attains a velocity of v. So this is our final velocity. So our final velocity is BC, right? So BC is the final velocity of the object. AO is the initial velocity of the object. OC is the time that the object is taking in order to attain the velocity from the initial velocity and reaching the final velocity. How much time does it take? It takes t time, right? Now here in this case, the velocity increase is increasing uniformly, which means that if you look at this part of the graph, the AB, this part of the graph, it gives you a slanting line. What does it tell you? That the velocity is increasing, but it is increasing at a very uniform rate. So it's a uniformly the velocity is increasing, right? Or we may say that suppose here let's say velocity is 10. Now after 1 hour again the velocity is 20 kilometers per hour or meters per second. After another 1 hour it is 30. So it is increasing, but it is increasing at a certain rate, okay, at a uniform rate. So this is the kind of graph that we will be considering and we will be discussing while explaining or while deriving the three equations of motion. Okay, so let's move ahead. Let's first discuss the first equation of motion, and for that the same graph is what we are going to consider, and I'm drawing the same graph over here. So this is your velocity and this is your time here on the x-axis, and this is how the graph looked like, and it was like this. So this is your O, this point is your A point, here you had B, okay, this is your B, and if I extend this line something like this, something like dashed lines, if I make it here, then this point I will take it as D, and this point is C. So this is the graph that we just learned. Now in this graph, whenever you want to derive the first equation of motion, first what you got to do is you have to write what is your BC. So how can you write this BC in terms of BD and DC? So you can write BC is equal to BD plus DC, isn't it? You can actually split them. BC will be equal to BD plus DC. Now what is BC? I already told you this BC is nothing but V, this is U, right? Now BC you can write V, which is equal to BD is something that you need to know, you do not know as of now, plus This DC is nothing but it is equal to U, because understand that this DC is equal to this OA, because both are opposite sides, so they are equal. So from this first equation I can take out what is my BD. My BD will be equal to V minus U, so I will take it as my first equation, right? I'll keep it aside. Now we also know that from the definition of acceleration, we know that what is acceleration. We have learned it is the change in velocity. It is the change in velocity divided by time, right? Now in this graph, how is the velocity changing? What is the change in the velocity? Can I write change in the velocity as BD? Is BD, this portion, this BD, this small portion, is BD the change in the velocity? Yes, because what is BD? BD is nothing but it is final velocity, this BC minus DC. If you subtract these two, you will get BD. So I can write change in velocity, I can write it as BD, right? So it will become BD upon T, which is equal to, so this becomes my second equation. Now from the first equation and from the second equation, I will take out what is BD, okay? So, or I can, sorry, oh, my mistake. Okay, so let's, how did we write? We first drew this diagram. I'm really sorry about this. So it was like this. So this is O, this is A, this is D, this is C, and this was B. So first equation of motion that we wrote was, first I wrote BD, and we found out that BD is V minus U, which was the first equation. And then we wrote A is equal to change in the velocity, which was BD upon T, right? So from this second equation, I can actually take out my BD. My BD is equal to A into T. So this becomes my second equation now. So I can actually equate first equation is equal to second equation. I can equate both the equation because both have D in common. So can I write V minus U is equal to A into T? So this becomes my first equation of motion. Okay, so this is my first equation of motion. Right? And this equation of motion is known as velocity time relationship. This is called as velocity time relationship because it has velocities involved, V and U, and then it has time also, coming. So it is velocity time relationship, right? So this is simply the first equation of motion. Now let's move on to the second equation of motion. And for that, again, we will consider the same graph, right? And in this case, again, let me draw the same graph again. You must practice drawing this graph many times, then only you will understand it very, very clearly. So this is my time, this is my velocity here, this is my time, this was O, this point was again A, this is D, this is C, and this topmost point was B. Now, when I'm trying to derive the second equation of motion, this second equation of motion is called as position time relationship. It is position time relationship. So you will see that once I derive the equation, you will have position and you will have time coming in that equation, right? Now let's start to derive. So we have studied that whenever we have a velocity time graph, then if we calculate the area, it will give us distance or displacement basically. Okay, so in this case, we will calculate the area. So how will we calculate the area? We can actually divide this area into two. Okay, first is we can actually calculate this area of this triangle and then we can add this area of the rectangle. So that will become the total area under this velocity time graph, right? So let us first calculate this is area of triangle. What is a triangle? ABD plus area of rectangle, that is OADC. Okay, so I will add both the areas and then only I will be getting my final area. So on the left side I have area. When I calculate area, it becomes nothing but distance. So I will write area as distance actually, right? So what is distance on the left side? Okay, what is the area of triangle ABD? I can write it as half base into height. What is the base? Base is AD into, what is the height? Height is BD. So I can write my area as half into AD into BD plus what will be the area of this triangle? I can write the area of triangle as OC into DC. Okay, I can write it like that. Now let's substitute the various values. So when I substitute the values, half into AD into BC, so half I will write as it is. What is my AD? What is my AD? My AD, I can write it as T. Why? Because this is nothing but T. Okay, because AD is parallel to OC. So I can write AD with nothing but equal to OC, which is time. So I can write half T into. Now what is BD? If you remember the first equation of motion, what was our first equation of motion? Our first equation of motion is V minus U is equal to AT, or I can write, if you remember, we had also written BD is equal to AT. You can go back and see BD is equal to AT, which was a second equation, you know, where while we were deriving the first equation of motion. This was the second equation. So I have to substitute this BD as A into T here. Okay, as A into T here. Now coming back to our area of rectangle OC, again what is OC? I can write OC as T into, what is DC? DC is U, because this DC is parallel to this OA, and OA is U, so I can write U. So if I solve this, I will get half A T square, because T into T becomes T square, plus UT. So my final equation becomes UT plus half AT square. So this is my second equation of motion. I have simply calculated the area of triangle and rectangle and added them up. Okay, and one more very small value that I have substituted is of BD, which you have to remember. So BD, the value has to be taken from the first equation. Okay, so this is how we derive the second equation of motion, or the position time relationship. Got it? Now next is we are going to actually learn to derive the we will learn to derive the third equation of motion, which is the last one, and it is also known as your position velocity. So again, let us learn to draw the graph a third time. So this is how the graph look like. Again, along with me, you should memorize. Okay, on the y-axis you have velocity, on the x-axis you have time. This is your O, this is A, here you had B, this point is D, this point is C, this is U, okay, and this one is V. Now in the third equation of motion also we have to calculate the area. Okay, but in this time the area is going to be the area of the entire trapezium. So this is the area. This time we are not going to divide the area into triangle and rectangle, but we are going to only calculate the total area of trapezium. So again we are going to write the area here. Okay. So what is the area of trapezium? The area of trapezium is, first you add both the heights. So this is AO plus BC and divided by 2 into OC. So this is the area. So both the heights you add, divide by 2, multiply by this distance, which is OC. So this is the area of trapezium. So again we have to substitute values here. Now in this case, what is OA? So left side will be area. Actually, area is in bar. It is this space which is going to give us this all these places. So which is nothing but position again. So I will write as what is OA? OA is U plus what is this BCC? What is going to be BCC is my final velocity divided by 2 into OC. OC is my time. So this is my equation. Now in this equation, we have to substitute the value of time. So here the catch is substituting the value of time. Now from the first equation of motion, we know that V minus U is equal to AT. So from this equation, substitute the value of T as V minus U upon A. Substitute this value in this equation. If you substitute the value, you will be getting S is equal to U plus V upon 2 into this is V minus U upon A. Okay. So now look at this. This is V minus U. This is V plus U. So what is the mathematical formula? It is V square minus U square. You know the formula of A square minus B square. A square minus B square is A into B multiplied by A plus B into A minus B. So I will write that formula here for you. So you already know that it is A square minus B square is equal to A plus B into A minus B. So that is the formula. So same formula I am actually substituting here also. Okay. So let me just substitute the value here and then you will know. Okay. So you will get V square minus U square upon 2A, right? And on the left you have S. So if I take this 2A on this side, you will get 2AS is equal to V square minus U square. So this is my third equation of motion. This is my third equation of motion. So these are the three equations of motion which you must know and you must learn how to derive them. Okay, and so I hope you've understood the three equations of motion. Maybe in the next video we will continue and learn how to substitute these three equations, how to substitute various values in these three equations of motion, and how to solve numericals based on three equations of motion. So